We're going to solve past paper questions of topic vector. This question is from the paper 2012, May, June 2-3. Okay, the first question is explain the difference between the quantities distance and displacement. So, distance, displacement is vector quantity, whereas distance is scalar. Okay, and distance is path followed and displacement is shortest path. State Newton's first law, it's law of inertia. A body continues at rest or at constant velocity unless acted upon by some resultant force. Okay, this is law of inertia. In the part C, two tug pulls a tanker at a constant velocity in the direction xy. This is the xy direction, and as represented in the figure 11.1.1, tug 1 pulls the tanker with a force T1, this is T1 here, at 25-degree angle to xy. Tug 2 pulls the tanker with a force of 15 degree, this is tug 2. The resultant force R due to the two tugs is 25 into 10 to the power 3 Newton. Okay, so this is the resultant force at the middle. That is also given, okay, in the xy direction. By reference to the forces acting on the tanker, explain how the tanker may be described as being in equilibrium. Okay, so basically there are two forces acting on it, the tug 1 and tug 2 force. If we resolve these forces into the components, this will be a x component of this force, so this is T1x, and its y component will be like this will be T1y. And if I resolve the second force, its x component will be this is T2x, and y component will be in this direction, this is T2y. Okay, so the tanker should be in the equilibrium as T1 and T2 are opposite in direction to each other, so sum of, and we can say that y component of T1 and T2 are equal, whereas sum of x components, these are the sum of x component, okay, T1x and T2x, both are acting in the rightful direction. Okay, so to balance them, there should be a equal and opposite force. So if the tanker is moving on a road, the opposition force can be a force of friction. Okay, so we can say that equal, whereas sum of x components of T1 and T2 must be equal to friction. Okay, only in that case the tanker can be in a equilibrium condition. Okay, in next part we have to complete figure 1.2 to draw a vector triangle for the forces R, T1 and T2. Okay, R is given, you have to draw T1 and T2. Okay, looking at the figure, we have T1, its angle is 25 and its magnitude of force is it given? Yes, T1 is this. Okay, magnitude is not given, but the angle is given. Okay, so let's start the T1 at this point. Its angle should be, you have to measure it with the help of D, 25 degree. I am making it approximately 25 degree, so it will be like this. This is T1 at the angle 25 degree. Okay, from head to tail rule, you have to draw the first vector. At the head of the first vector you have to place the second vector. Second vector is this T2, and T2 is acting downward from the x-axis 15 degrees. Okay, so 15 degree downward. So first of all we have to make a imaginary line here. Let's suppose this is the x-axis, and you have to check with the D the 15 degree angle. Let's suppose this is the 15 degree and you have to draw a line that will meet at this point. Okay, so this is T2 at 15 degree angle. Now use your vector triangle in figure 1.2 to determine the magnitude of T1 and of T2. Okay, so first of all we have to measure this line that is drawn for R. Okay, you have to measure it with the help of scale, and that, let's suppose that measure value is x centimeters. Okay, on the scale, so x centimeters are equals to 25.0 10 raised to power 3 Newton. Okay, so 1 centimeter will be equals to 25.0 10 raised to power 3 divided by x. Okay, so this will give you a scale. From this thing you can get the scale, and then what you have to do, you have to measure a length of this line from here to till this point. Let's suppose its length is L1. Okay, L1 centimeters. You have to multiply this thing with the L1 multiply by scale, give you the answer in Newton. Same goes for this one. You have to measure this length from this point to this point with the scale. Let's suppose this length is L2 centimeters. Then you have to multiply L2 with scale. That will give you your answer in newtons. Okay, so this will be the magnitude of T1 and T2. Okay, let's move toward the next question. In question number 2, this question is from paper 2012, October November variant 2-3. Spacing between two atoms in crystal is 3.2 into 10 raised to power minus 10 meters. State the distance in picometer. Okay, so we have to convert it. Basically pico is 10 power minus 12, so I have to make it minus 12. So 3.8 into 10 raised to power minus 10. What I have to do, I have to make the power minus 12, so I have to divide it by 10 power 2. Okay, and if I am dividing it I have to multiply as well. So this factor, when they combine together, they will make 3.8 10 raised to power minus 12, and leaving this thing as it is. Okay, now this thing is a pico. Okay, so it is 3.8 into 10 raised to power 2 picometer. So it can be written as 380 picometers. Okay, 10 power 2 is equals to 100. In the part B, calculate the time of 1 day in megaseconds. Okay, so in 1 day, um, what we have 24 hours. In each hour we have 60 minutes. Each minute we have 60 seconds. Okay, so this is the time in second in 1 day. Okay, this is 1 day. So this will give you, this is 36, so 24 into 3600. Okay, we have to convert it into mega is, m is basically 10 power 6, or what we can say 1 2 3 4 5 6. Okay, so if I have to write down mega, I have to multiply and divide it. Okay, so writing down mega and dividing with 1 and 6 zeros. Okay, so this will give you 0.086 megaseconds. In part C, the distance from the Earth to the Sun is 0.15 terameters. Calculate the time in minutes for light to travel from Sun to the Earth. You have to calculate the time in minutes. Okay, so using the basic equation, S is equals to V into T, T is equals to S divided by V. S is basically 0.15 tera, so it's 0.15 tera is 10 power 12. Okay, and speed of this C is V is speed of light. Speed of light, that is 3 into 10 raised to power 8. Okay, dividing both of them, you get 500 seconds. You have to convert it into minutes, so for converting into minutes you have to divide it by 60. That will give you minutes. Okay, 500 divided by 60, it's 8.3 minutes. Part D, underline all the vector quantities in the list below. Vector quantity: distance is not, energy is not, momentum is vector quantity, weight is a vector quantity, work is not. Okay, in part E, the velocity vector diagram for an aircraft heading due north is shown the scale to scale in figure 1.1. There is a wind blowing from the northwest. The speed of the wind is 36 meter per second and the speed of the aircraft is 250 meter per second. Draw an arrow to show the direction of the resultant velocity of the aircraft. Again, it's a own scale diagram. You have to measure it properly and make it on a paper. Okay, just for the guideline, what we have to do first, we have to draw a direction of resultant force. Okay, by head to tail rule, we have to draw the first vector in the same direction as it is given in the question. Then you have to place the second vector, the tail of the second vector, on the head of the first. Okay, so let's suppose this is first one and this wind is the second one. Okay, so I have to place, and if I consider this first vector here, this is the first vector, this is its head, I have to place the tail of the second vector on the head of first. So this is the tail of the second vector. Okay, so this tail should be head of the first and its direction should be 45 to the x-axis. Okay, so let's make it here. Okay, so if I, this is 45 degree, so it will move like this. .45 degree angle. Okay, so it's like this. The resultant will be from the tail of first. This is the tail of first, and this is the head of last. Head of last. Okay, so resultant will be from the tail of first to the head of last. This is the direction of resultant. If you make it exactly on scale, you can calculate the magnitude as well by just measuring the length with the scale. Determine the magnitude of the resultant velocity of the aircraft. Okay, so for the magnitude, what you have to do, you have to measure this length, and you have to find out the scale from this diagram. Okay, you have the speed of aircraft, you have to find the scale from this diagram and multiply this scale with this length. You get your answer. In question 3, it's question from 2013 paper, May June 21. Distinguish between mass and weight. Okay, so mass can be is a quantity of matter, whereas weight is force due to gravity on object. Okay, in part B, the object O of mass 4.9 kg is suspended by a rope A that is fixed at point P. The object is pulled to one side and held in equilibrium by a second rope B as shown in the figure. Okay, a rope A is at angle of theta to the horizontal and rope B is horizontal. The tension in the rope A is 69 Newton. Okay, the tension in the rope B is T. Draw arrow to represent the direction of all the forces acting on the object. Okay, so tension, this is the object. Okay, and this is the rope. Tension is always towards the fixed point. Okay, the thing that is holding the object, holding point is this one. Okay, at this point the wall is attached, so the tension will be toward that holding point. This is the direction of force, and there will be some holding point, so there will be a direction of force. Okay, so this is for the draw arrow to represent the direction for the forces acting on the object. Okay, third force will be, there will be another force on it. That force will be the force of weight. Okay, the object weight. Calculate the angle theta. Okay, so we have to calculate the angle theta from this end. This is in the equilibrium state. Okay, so first of all, I have to check the vertical components. Okay, in vertical direction, there is one force, that is weight. Weight of the object is mass is given. Okay, so weight is equals to 4.9 into 9.81. That is downward acting force. Okay, and for the equilibrium, there must be a upward acting force. And what is the upward acting force? This tension in rope B is totally in the horizontal direction, so there is no contribution of that rope in the vertical direction. Only this rope A is in the XY plane. Okay, so you have to you have to find out its component. So to finding it component, it's this will be its X component. This, let's suppose tension in A, its X component, and this will be its Y component. Okay, so for the equilibrium, this tension in AY must be equals to its weight, and multiplying this, it will give you, this is equals to 48.07. okay, so it's 48.07. Okay, so y component will be t sine theta is equals to 48.07. T is the value of, what is the value of tension? It's given tension in rope A is 69. Okay, so it's 69 sine theta is equals to 48.07. So sine theta is equals to 48.07 divided by 69. Theta is equals to sine inverse 48.07 divided by 69. The answer will be 44.1 degree. Okay, 44.1 degree. Okay, now you have to find the tension T. Okay, for tension T, we have to find. Okay, tension T is this one in the B. Okay, for the equilibrium, the x component of tension A must be equals to this tension B. Okay, for the equilibrium condition. So for this case, let's solve it at this point. For this case, tension T AX must be equals to tension. Okay, there is no x or y component, is totally in the horizontal, so it's simply T. So TAX is equals to T A cos theta. Component attached with the angle is always cos, and the opposite one will be sine. Okay, so it's cos theta is equals to T. So TA is given, that is 69, and cos theta is also, we have already found, it's 44.1, that is equals to T. So solving the values, we get T is equals to 49.6 degree, or we can say 50 degree. Okay, so tension is, sorry, it's not degree, it's Newton, it's not angle. Okay, it's Newton. Okay, starting question number 4. In question 4, it's from 2014 October November 23. Force is a vector quantity, state 3 other quantities. Okay, so you have to write down 3 other vector quantities. It can be displacement, it can be acceleration, it can be momentum, it can be velocity, and there are many other vector quantities you can write down. In part B, 3 coplanar forces x, y, z act on the object as shown in the figure. Force z is vertical, this is z force, and x is horizontal, this is x force. The force y is at angle of theta, this is y. The force z is kept constant at 70 Newton. Z force is 70 Newton. Okay, z is 70 Newton. In an experiment, the magnitude of x is changed. The magnitude and the direction of y are adjusted so that the object remain in equilibrium. Okay, so this is in equilibrium, you have to keep in mind. So show the variation of magnitude of y and x. This is a graph that we have. This is the response of the graph. Okay, use figure 3.2 to estimate the magnitude of y for x is equals to 0. Okay, so where is x? This is x. So x will be 0 on y-axis. Okay, so you have to estimate. If you produce this graph, this will eventually go toward this. Okay, so at this point x is 0. Okay, so at this point value of y is 70, so estimate is 70 because the graph is going toward this side. Okay, it is the slope is 0 almost at the start. It's the estimate. State and explain the value of theta for x is equals to 0. Okay, for x is equals to 0, you have to tell the value of theta. Okay, so if x is 0, let's suppose there is no x force and this object should be in equilibrium, then and there is a 70 Newton force. Let's consider this is the object. There is a force z that is 70 Newton. You can apply another force y, but the condition is you have to the object should be in the equilibrium. Okay, so there is the second force y should be exactly in the opposite direction to balance it. Okay, otherwise it will not be balanced in any other condition, in any other direction. So the value of this theta will be 90 degree. Okay, that is the case. So this, if this x force is removed, this y should be applied like this to balance this z force. Okay, so the angle will be, in that case, it's 90 degree. Theta will be 90. So that you have to tell. Okay, so if state first, we have to write down the angle. Theta will be equals to 90 if we remove x force, then y should be exactly opposite to z to balance it. Okay, there is no other condition. The magnitude of x is increased to 160 newtons. Use resolution of forces to calculate the value of theta. Okay, so now the value of x is 160. We have to find theta. Value of x is 160. This is equals to 160 newton. We have to use resolution of forces to find value of theta. It's third B. Okay. Okay, so it's 160. So for 160, this force is totally in the x-axis. This is totally in the y-axis. We have to, it's in the equilibrium condition. So first we have to find out the component of this force. The x component of this force will be in this direction. It will be y cos of theta, and y component will be, y is the force basically. Okay, it's y component will be y sine of theta. Okay, for the equilibrium, this x component should balance each other and y component should balance each other. So it will be y cos theta is equals to 160 newton. Okay, these two forces should balance each other, and these two forces, the y-axis forces, they should balance each other. So, and y sine theta must be equals to 70. Okay, what we have to do, we have to find theta. So these are the two equations. Let me write down here. It's, I have y sine theta is equals to 70 and y cos theta is equals to 160. Okay, so these are the two equations. We can divide them. If you divide them, this y will cancel out. Sine theta over cos theta will be tan theta. tan theta is equals to 70 divided by 60. 70 divided by 60, 160, sorry. And we need theta. Theta will be tan inverse 71 by 160. This will give you 23.6 degree. So it can be written as 24 degree, okay? Roundabout value. Question number 2, you have to find the magnitude of the y force. Okay, so to find the magnitude, what we have, we can use any one of the equation that we have, any one of the equation from these. Let's suppose we use this equation, y of sine theta is equals to 70 degrees. So y is equals to 70 divided by sine theta. So 70 divided by sine of 24. This will give you 170 Newton. Okay, so 170 Newton is the answer. In part C, the angle theta decreases as x increases. Explain why the object cannot be in equilibrium for theta is equals to 0. Okay, they're telling us that the angle theta decreases as x increases. Okay, this is the figure. If x increase, the theta will decrease. Okay, basically, if you see, if you increase the x force, so you need a greater x component of this force to balance it. So this force should be more inclined toward the x-axis if you want to balance it, balance the other x component of the force. Okay, so as you increase the x force toward the left side in the horizontal component, the y force, the x component of the y force should also be increased to balance it. That is why you have to decrease the theta. Okay, so the more force will be toward the horizontal side. So why it cannot be explain why the object cannot be in equilibrium for theta is equals to 0. Let's suppose if theta is equals to 0, let me, is it, let's suppose if theta is equals to 0, it's mean this force, the y force is not at this point, it will be acting at this point. Okay, so this y can balance this x, but there is no component to balance this x force, so this z force. Okay, so it will not be balanced, it will not be in equilibrium. You need y component and x component both to balance this x force and z force, because x is acting in horizontal position and z is acting in vertical position. So this should be in xy plane, it should have x component, y component to balance these two forces. Okay, so the answer is, if theta is equals to 0, there is no vertical component